The nature of energy. So chemistry is the study of matter, and energy affects matter. So studying energy definitely falls into the realm of chemistry. What is energy? Well, scientifically, energy is anything that has the capacity to do work. It doesn't actually have to do the work, but the capacity to do work. And in science, we define work a little differently than how we use it in that word in everyday life. Work is a force acting over a distance. So we could say that energy is equal to work. Work equals a force times a distance. So when I pick up, oh, I could drop these. When I pick up my safety goggles from the bench and move it up, I'm opposing the force of gravity with the mass of these goggles. I'm doing work. If I push it across the bench, I'm applying a force across a distance, and that is doing work. Heat is the flow of energy. Heat is the flow of energy caused by a difference in temperature. So energy can be exchanged between objects through contact. In my periodic table of the elements cup here, there are ice cubes floating in the water. There is a transfer of energy occurring based on temperature difference. I just put tap water in there. The ice cubes are colder, so energy is flowing in the form of heat from the water to the ice cubes. But energy can also be exchanged through collisions.
So ice is an exothermic reaction, right? The
Ice melting is endothermic.
Endothermic?
Because, and we'll get to this, you have to take the position of the ice. What's happening with the ice? The ice has energy coming in, and that's endothermic.
So
The water is experiencing an exothermic process where its energy is going out.
yeah, exactly.
So you always have one or the other, one and the other. You have energy flowing in one direction, but how the different parts experience it is opposite. So we need to think of energy as a quantity that can be possessed by an object or a set of objects. So it's a little bit like money. You can have money, right? And you can transfer money to other people or to different parts of your banking system through your savings or checking account. So energy is like money. Heat and work are the ways that those objects can transfer energy. Okay? Energy can move out of an object or into it. Money can leave your checking account or come into it. Money can leave your wallet or come into your wallet. Your wallet would be the object, and the money is the energy that's coming in or out. So we classify energy, of course, because scientists classify everything, right? Kinetic energy is energy of motion. An object that is moving has kinetic energy. Thermal energy is a form of kinetic energy. Thermal energy is the energy associated with temperature. And that doesn't seem immediately obvious. How can thermal energy, how is temperature associated with movement, right? A hot cup of tea does not appear to be moving. But when you look at the individual particles that are in the tea, the reason that it's hot is those particles are moving faster. When we have the hot plates out and that porcelain top of the hot plate gets hot, because that's what the purpose of it is, it doesn't look like it's moving, but the individual particles in the porcelain are vibrating and oscillating faster than they are when it's cold. And that's what causes it to feel hot. It has more energy, and we experience that as a hotter temperature. That's thermal energy. So here we have an illustration of a billiard table, and we have the cue ball rolling quickly towards another ball. This cue ball, because it is moving, has kinetic energy. When it hits this other ball, it transfers its energy to the other ball. And the other ball then moves, and now that the energy was transferred to the other ball. The way it was transferred was through the process called work. That transfer of energy doesn't have anything to do with temperature, but it does have to do with a force. Any questions yet? If you have questions on this stuff, ask right away, because I'm assuming that you're understanding what we're talking about as we go along, because it's going to get more involved. So there's kinetic energy, and then there's potential energy. So potential energy has to do with the position or the composition of an object. If I take this eraser, this is a good thing to drop. So if I take this eraser and I lift it up high, it has more potential energy than if I hold it down low. If I'm holding it up here about as tall as I am and I let go of it, that kinetic energy that we see as it's moving, where did that come from? It's the transfer of the potential energy into kinetic energy. Now that it's on the floor in a pile of chalk dust, it has less potential energy than it did when I was holding it up. Here, the illustration of dropping the billiard ball. Gravitational potential energy. When we lift something above the earth, it has greater potential energy because when we let go, every single time it goes down. And the potential energy gets transformed into kinetic energy, the motion of the ball moving towards the center of the earth. Chemical energy is a form of potential energy. Just like thermal energy was a form of kinetic energy, chemical energy is a form of potential energy. This doesn't have to do with position above the surface of the earth, but has to do with relative positions of atoms and molecules within a substance. Because of the positions of the atoms, there is energy stored inside the compound. So this is a summary flow chart. Energy, the capacity to do work. We've got kinetic energy and potential energy. Kinetic energy is related to motion. Potential is related to position or composition. And the form of potential energy we're most interested in chemistry is, of course, chemical energy. Energy associated with positions of electrons and nuclei, relative positions of atoms. Energy due to motion, the subcategory we're interested in is thermal energy, and that is associated with temperature, which is a reflection of the movement of the particles in a compound. Other forms of energy. We're familiar with electrical energy. This is kinetic energy associated with the flow of electrical charge. So electrons are moving. My computer is plugged in, and today the outlet is working. There's electrical energy going on because the electrons are moving. Heat or thermal energy, we already talked about that. This is kinetic energy associated with molecular motion. Electrical energy is electrons moving. Heat or thermal energy is the molecules or atoms moving. We have light or radiant energy. The light from the fluorescent lights in here doesn't seem to have all that much energy, but you go outside when the sun's shining and you can feel the energy that it's transferring to your skin. This is energy associated with energy transitions in an atom. And we'll look at that later when we talk about what's going on inside of atoms. Nuclear energy, potential energy in the nucleus of atoms. Chemical energy, potential energy due to the structure of atoms. Attachments between them, relative positions. The law of conservation of energy states that energy cannot be created nor destroyed. So when energy is transferred between objects or converted from one form or another to another, the total amount of energy is conserved. It's the same. Energy cannot be destroyed or created, but it can be transferred and exchanged into a less useful form of energy. And that's why we see an apparent loss of energy. It gets transformed into something like thermal energy, which isn't always very useful. In this illustration, this woman is pressing down on a ball on top of a spring. And as she presses down, she's giving mechanical potential energy to this ball by compressing the spring. It's not a string. And when she releases it, that mechanical potential energy is converted into kinetic energy, and the ball shoots up into the air. When we talk about energy transfers, we have to carefully identify where the energy is coming from and where it's going to. And so we talk about the system and the surroundings. And those definitions can change. Even when you're talking about the same set of circumstances, you can look at different parts of it as being the system. The system is the piece of the universe that we're interested in looking at. It could be a beaker, it could be a chemical reaction, it could be an ice cube. It's something that we are interested in, what's going on with this piece of the universe. And the surroundings is everything else in the entire universe. Usually we don't have to think about the whole universe, usually just the immediate surroundings are good enough. But what we're studying is the transfer of energy between the system and the surroundings. So conservation of energy means that the amount of energy gained or lost by the system, whatever it is that we're looking at, has to be equal to the amount of energy lost or gained by the surroundings. It's like transferring money from your checking to your savings account. If I define the checking account as the system, the savings account as the surroundings, money that leaves the checking account is going into the savings account. Does any get lost in that transfer? Not if your bank is decent, right? Nothing should happen. And if you transfer money from your savings to the checking, if you look at the savings account as the system, the money's leaving the savings account, it goes into the checking account. No money is lost. So here we have little energy gauges. If we start out with the system and the surroundings, where the system has half full energy and the surroundings is a quarter full. And we have a transfer of energy from the system to the surroundings. The surroundings are gaining the same amount of energy that is lost by the system. Now, the energy does not have to be in the same form, but the amount of energy is constant. Does that make sense? This has direct application to the experiment we're doing in lab today. Well, energy is something that can be measured, so of course we need units. The amount of kinetic energy that an object has is directly proportional to its mass and its velocity, and we saw this equation in chapter 5 as well. Kinetic energy is 1/2 mass times the velocity squared. So it depends on the mass of the object and how fast it's moving. The joule is the metric system of metric unit of energy. That's the word. Joule, Joule, abbreviated capital J. It's a relatively small unit, and we can apply metric prefixes to joule in the same way that we do for other units. So a kilojoule is 1,000 joules. Here, this is just an illustration. A typical light bulb will use 3.6 times 10 to the 5th joules in an hour. Sounds like a lot. Yeah, the joule is a very small unit. That's only 0.1 kilowatt hours. Kilowatt hours are another unit of energy that the electric company uses, but we don't use them in chemistry. So the unit joule is defined in terms of other SI units. It's the amount of energy needed to move a 1 kilogram mass a distance of 1 meter. And this has to do with that definition of work, right? Energy is the capacity to do work. Work is a force times a distance. So here is, it's 1 kilogram, 1 meter. So it's a force of 1 Newton times a distance of 1 meter. And a Newton is a kilogram meter per second squared. And so a joule is equal to kilograms meters squared per second squared. That's a very messy combination of units, and that's partly why we gave it the name joule, is just to sort of simplify that. A calorie, you've probably heard of calories. That's the amount of energy needed to raise the temperature of 1 gram of water 1 degree Celsius. That's a different sort of an energy definition. But they're both measures of energy. So the relationship between them is that 1 calorie is equal to 4.184 joules. And that's an exact conversion. So when we're converting between calories and joules, that's not going to affect the number of significant figures. The calories that we're familiar with are the nutritional calories. That's a calorie with a capital C. So capital C, lowercase c. It's different by a factor of 1,000. So a nutritional calorie is actually a kilocalorie in terms of scientific calories, or 1,000 small calories. So the calories we're going to be talking about are these regular ones, not the nutritional ones. But it could come up like on an exam or on the final or something, and that capital C is not a typo. It's a significant indication that you're dealing actually with kilocalories. Here are a couple of interesting tables from your book, just kind of comparing these different units. So a calorie is 4.184 joules. Nutritional calorie or kilocalorie would be 1,000 calories, 4,184 joules. And if you should need it, there's a relationship between kilowatt hours and joules. Amount of heat energy needed to raise the temperature of 1 gram of water, to light a light bulb, 100-watt light bulb for an hour. Amount used by the human body when running 1 mile. So that's always so discouraging. You could run for a mile and you're only going to burn 100 nutritional calories. That's part of why I don't run. It's not worth it. And then how much energy is used by a U.S. citizen in 1 day. So just for your interest.